Okay, welcome to the first talk of this session. It's my great pleasure to introduce you to Professor Alexey Bondal from Steklov Mathematical Institute. He's a well-known mathematician, one of the world-leading mathematicians, especially by the work on derived categories of sheaves on algebraic varieties, and which uncovered very deep connections between the derived categories and classical algebraic geometry. But probably he's going to talk about something a bit different today. And he will talk about, a categorical and geometrical approach to matrix multiplication complexity. Let's welcome Professor Alexey Bondal.
Thank you. Yeah, whenever I start some problem, even if it's very far from derived categories, eventually it's finished with derived categories. So this problem will also have something about derived categories. So thank you very much for inviting me to this tremendous mathematical event. So I will speak about it's called computational complexity of matrix multiplications. It does not need extra advertisement because on this congress there was two groups of researchers who got who got awards in the category of how it was called scientific scientific computing. Was it this way? Anyway, and it was about matrix multiplication. But I will try to, the goal of my talk is to give such a sort of new approach, I would say a new direction of research, which I hope will attract attention of people here and not only here. So but I will say a few words about what is matrix multiplication about. So we want to multiply matrices. So we take two matrices A and B, and my n matrices over, well, for simplicity, I will assume it's complex number somehow. It doesn't matter. And then we want to multiply them, A cross B. Everybody studied as the first year of undergraduates, right? So this is some new matrix C. And to calculate this matrix, we should multiply columns by bottoms, right? So this matrix has n squared entries. And to calculate every of this entry, you need to multiply one column, one row from here, right, and one column here. So it's for every entry of C requires n multiplications. We consider multiplication as more complicated. I mean multiplications of entries of A and B, right? Row by column, n multiplications, right? Cij equals to sum of A ik bkj. So for I is from k is from 1 to n, so that's why it's n multiplications. So to calculate this matrix, we need n cube multiplications of elements of matrices A and B. It was Volker Strassen who found that if you multiply 2 by 2 matrices, then you actually need not 8 but 7 multiplications of these guys. If I actually try to prove that not less than 8 multiplications is possible, come to the finite fields to construct some invariant. Or the finite fields, he take p equals 2, 3, 4, 5, so on, and all this, his invariance didn't work. And then he realized that actually 7 multiplications is enough. So question, the main problem, how many multiplications we need for it was later proven that 7 is actually the minimal number of multiplications. So the question is how many multiplications we need for n by n matrices. And the answer is not known even for n equals 3. So let me denote this this number by mn. So m2 is 7. M3, it is known that it's between 19, the low bound, and the upper bound is 23, I think. So it's still not known what is exactly this number. For m equals 4, there is some recent result of some artificial intellect who found that at least over some finite fields, it found an algorithm which shows which use only 44 multiplications. But it's over finite fields. So I don't think it's approved over complex numbers. So. But it does improve when you consider non-square matrices, if I understand correctly. So in this area, we should fight with the artificial intellect, and I believe it might get some upper bound, but not low bound. And my talk will, in particular, about low bounds for this number. So let me now reformulate this story in a more mathematical way, so to speak. So let's consider, so what is this multiplication of matrices? It's after all some, so we consider, it's bilinear operation, so we can consider it as a map from these guys into this one. So it's some, I already used this m. Okay, let it be mu n. So it's a bilinear map, so it could be defined as such a map. So let's consider more general case when we replace this space by u, this by probably another space v, and this by the third space w. So it's 3 vector spaces, and we consider some phi here. This phi is actually an element from u star, tensor v star, tensor w. So it's a how it's called 3-way tensor or trilinear tensor. And now the problem actually about this number of multiplications is about the rank. So rank, in this case, about rank of mu n. It's equivalent. And the rank is just the number of, it's a trilinear tensor. The rank is the way how you can present this. So rank of f is the minimal S R, such that phi is the linear combination of phi i's, where rank of phi I is 1. Is 1, and rank of phi is 1. It means that it's a decomposable tensor. So it's kind of something like u hat tensor v hat tensor w. Okay. I mean, not every element here is like this. Only linear combinations are. So actually, this problem is about the calculation of rank of the multiplication tensor. Why? Because if you have such a decomposition, every such phi gives you actually use only one multiplication. So let's consider such phi, which is of rank 1. So it gives some map from here to here, and actually, if you think about it, it's just the corresponding map from UV to W is just given by, if you have here U, tensor V, then it goes to what? To U hat of U multiplied by V hat of V. It's just some scalar multiplied by W. So it's just vector multiplied. So you see here, it's just one multiplication here, nothing else. Just one coefficient in front of this W. So this is a reformulation of the problem, and surprisingly, one might expect such a basic problem, and mathematics should know how to solve it. But surprisingly, it's not even known what is the rank of generic tensor. So if you consider, say, K, L, M dimensions of U, V, and W, that for it's not known for all Km, KLM, the generic, the rank of generic tensor. Generic phi in U, right? It doesn't matter, but U, V, K, W. So even this, for some KL, KLA, KLM, we do know it, but not for all of them. And this is an open problem, which of course should be solved. In the 21st century, we still don't know it. So I will give some categorical approach to this problem and to similar problems. For instance, you don't need necessarily multiply matrices, but you might need to multiply polynomials. Still an open problem. Say polynomials in one variable in some degree. I think it's still not known. Again, it's a bilinear operation. So in this setup, it's kind of generalize all of them. So to approach this problem, I will interpret this phi as an object in some abelian category. So we are given again this phi in W. Let me consider it as a representation of a quiver. And the quiver has, well, quiver is what? It's you have some vertices, some arrows, composition of arrows, linear combinations might be trivial, quiver with relations. At this quiver will be no relations. So K is always the dimension of U. So I should consider quiver with two vertices and K arrows from the first vertex, say 0, to the second one, 1. Number of these arrows is K. Okay? So if you have a quiver, then you have the abelian category of representations of this quiver. In general, if you have a quiver, dimension vectors of the representation. But first, I would like to say what is representation. So it means that to every vertex you assign some vector space. So to every vertex I, you assign some vector space Vi. And to every arrow, you assign some linear map from the first from Vi to Vj. So this is a representation, just one representation. And if you have some relations, for instance, say assume the composition of these two arrows is 0, it's some relation in the quiver, then you should corresponding relation between corresponding linear operators in this representation. So if you consider all representations of a given quiver with, well, first of all, if you consider all representations of a given quiver probably with relations, Q is a quiver, then sorry, and I is the relations on the queue, which are linear combinations of some paths in the queue relations. Then mod Q. So we can consider algebra, which is the path algebra of the queue, meaning you consider all paths and the obvious composition of paths if they compose, and they are not composable, then you just assume them zero. For instance, if you consider this queue, and then composition of this arrow with this arrow is just zero by definition. But composition of this arrow with this arrow could be a new path, which might be zero or not zero, depending on your relations. So we consider Q of Q over I. So this is path algebra. Maybe I should write it this way. I don't know. No, I think this way. So it's a path algebra of the queue, this one. And these are modding out the ideal of relations. So this is some algebra A. And what I described here in naive way, it's actually a module over this algebra. So we can consider the categories, say, left. Well, usually if it's about representations of queues, it's the left modules. I should decide now. Okay, let it be left modules, meaning A mod. And it's some A, which is actually an abelian category. Meaning you have kernels, co-kernels, and kernel of co-kernel equals to co-kernel of kernel. Abelian category. Moreover, you might think it's very special construction, but in fact it's not. Every abelian category with reasonable properties, finiteness properties, is of this form. And every algebra, say finite dimensional algebra, is Morita equivalent to algebra of this form. So it's actually quite general. So in our case, we will consider this is for k equals 2, it's called Kronecker queue. And for n k equals 1, it's called A2 queue because it's Dynkin diagram. It's a queue with Dynkin diagram A2. And for higher k, it's kind of generalization of Kronecker queue. Why it's called Kronecker queue for k equals 2? Because Kronecker classified all representation in decomposable. I mean, you can take direct sums of representation. So in decomposable representations, which you cannot decompose into the direct sum, could be completely classified in this particular case, k equals 2. And we will consider this case, I hope. So now, why this thing is a representation of this queue? Well, these arrows should be understood as a choice of some basis in U. So I consider U. Somehow I made this, even though this tensor is sort of symmetric with replace of, and this definition of rank, it's symmetric with respect to perturbations of these three vector spaces. But I make it artificially non-symmetric by choosing one of the space U to be the space of arrows. And then when you choose this basis corresponds to this arrow. Somehow if you consider, you may consider this queue as actually as just a vector space. From 0 to 1, it's not just arrows, but the vector space, and this is just basis. And then representation is given by U, so this is basically U. If you choose basis, then it corresponds to the arrows. And then you have V and W. And then this tensor is exactly gives you representation of this queue, which is sort of obvious thing. Right, so, but because they make some abelian category, we can think about this problem of the rank, maybe, yeah, in terms of this representation theory. And surprisingly, at least I never seen this to be considered by people working in algebraic, in the representations of this associative, finite dimensional associative algebras of queries. So I will reinterpret this definition of rank in terms of the category of these representations. That would be my first goal. for this, I should consider some special special conditions. So let's M be a representation of this Kronecker QR. Let me denote it by Qn. So it has no relation, so it's just K of Un mod, the category which I consider, right? So I say that this representation is, I mean, I will later define for other QRs, but first we will study some analysis of what happens for this particular QR. So we say that definition, I call it, sorry, I forgot what I call it. Reduced, okay, reduced. Is reduced if M has no direct summons of simple modules, which are S0 and S1. These are simple modules, meaning irreducible objects in this abelian category, and they correspond to vertices of our QR. So QR has two vertices, 0 and 1. So S0 is a representation which is given by, so these are n arrows. So here we have K, which is our complex numbers, and here 0. And so this is representation for S0, and for S1 is similar, but one-dimensional space here, and zero-dimensional here. And of course, all arrows are represented by 0. These are simple modules, and in general, if you consider representations of QR, simple modules corresponds to the vertices of the QR. So I assume there is no things like this, and in our module, and then maybe I should also introduce yes, another definition. When one module, or maybe first one phi, so we have phi, which is again from U tensor V to W. So U is fixed, but I might vary V and W. So let I also have phi prime, which is from U tensor V prime into W prime. It's another representation of the same QR. So I will say that phi prime dominates phi if you have a diagram like this. So you have U tensor V tensor W, and there is some map from U is fixed, but from V to V prime. There exist alpha V and beta AV and BW. So AV is a map here. So we tensor it with the identity map on U. We map it here, but W prime, it's, I mean, BV, this is BW. So it goes in the opposite direction, such that this diagram is commutative. With strange definition from the point of representation of, but that's what actually related to this story. Now, yeah, also if I have several tensors, it's so extension. If I have several tensors phi I, then the family dominates. This was the definition. Sorry, definition of domination. So phi, the set of tensors is dominates some tensor phi if the sum of these phi i's, so phi I is from U tensor Vi to Wi, when we sum them up, because U is fixed, we just fix U, and we just sum up these representations if you want. So it's the sum of Vi's and goes, and the tensor is the sum of tensors into sum of Wi's. So we say that this family dominates this if this dominates phi, if this in this sense. Okay. Now the statement is, after some analysis, I don't know, it's not very hard thing, but okay, proposition. And yes, maybe thought we will. This was about tensors, but we can say the same about representations because we are going to speak about representations. So we say M dominates another module M if the corresponding phi M dominates. Corresponding tensor dominates phi n. So it's about domination of modules. And I want now to categorically interpret this domination in terms of representation theory. So theorem or proposition or whatever. Assume M is reduced, right? Reduced. Then N dominates M if and only if, maybe I should introduce more, if N belongs to, let me denote, it's kind of ideal with respect to the star product. Let me explain me. So we take ideal, two-sided ideal generated by M in the sense of the star product, the notion which was probably first considered by Gabriel, an expert in abelian categories. But I'm not sure if he was the first one. Somebody told me it was somebody else. So let me explain what is the star product. So it's the following. Assume you have two subcategories. In some abelian category, consider two subcategories, B and C. Closed with respect to direct summons, if I respect full subcategories, then we can define B star C. It's a new subcategory in A, which consists of objects A in A, which have a decomposition into short exact sequences like this. So A has a subobject which is an object in the category B, and C is a object is a quotient object of A, which is lies in the subcategory C. Okay. There is similar definition for triangulated categories, which was first appeared in the book of Pervers Schiff's by Deligne, Beilinson, Bernstein, Deligne, and which we will actually keep in mind. And this is kind of extension of this one. So if, for instance, if instead of category A, you consider derived category, the definition is basically the same, just you replace this by triangle, BAC. And these are these two definitions for abelian category and for derived category matched in the sense that abelian category is embedded into derived category. So if you consider it's a full subcategory, if you consider this notion on some subcategories in B, it would be the same for triangulated. So we can use derived equivalence to discuss this subject. And now maybe I'll show on simplest example how to do this. So you see, you start with very classical problem in computational complexity and come to the derived categories. It's always like this with me. Sorry for this. So, how it's related to the rank? Yes, so did I understand, explain what is this? This is objects. This is again some subcategory whose objects lie in the two-sided ideal, so to speak, with respect to this multiplication. When you multiply this M on other side by other objects with respect to this star. So objects like this. So here's some L1 and here's some L2. This is just notation for the subcategory of these objects, where star is defined in this way. Or similar thing in triangulated categories. So why it's related to the rank? Because, yeah, for this I should consider rank 1. Rank 1 representations are the following. It's for this Kronecker cure, it's just we have this U or basis of them, and we consider one-dimensional space here and here. So these are actually rank 1 phi's or modules. And now the claim is that the rank of arbitrary, yeah, well, there is several statements. For instance, first is the rank of M. Well, I didn't say what is M reduced, but there is obvious reduced version of a module. You can just mod out all simple submodules. No direct sum, so we can kill all these direct summands, and it's obvious how to do it at the level of the corresponding tensor. So rank of M is equal to rank M reduced. That's one statement. And second statement is that rank of M equals to minimal k such that the sum of mi's, the direct sum of mi's dominates M such that rank of mi is 1. So domination is about this. First, we should fix some, if we want to generalize it, we should consider some set of objects which we call rank 1. In this case, it's just, we consider every this mi, I mean rank 1. Let me call ni, not mixed up. So every such n rank 1 module is what? It actually has an extension. So this is 0, this is 1, this is S0, and this is S1. So it's a simple extension, one simple module. I mean, it's an extension of one simple module by another simple module. Am I correct? Yeah. So we should consider the set of rank 1 modules, and this in this case it's just extensions. Simple one by the other one, not the sum of them, but it's important because every module is an extension of sum of S1s by the sum of S0s. So we should fix the set of rank 1 modules and then consider this domination property by the sum of this rank 1 modules over all k. So I is from 1 to k, sorry. So minimal k such that the sum of modules dominates this M. This is very, I would say it's very surprising. I never seen anything in the representation theory of finite dimensional algebras or something like this. And I'm going to analyze this property and generalize it in my talk. But maybe first, because we already interpreted categorically, I will give some examples. And this is when the number of arrows Qn, when it's Kronecker Q. So it's this one. All representations for this queer are well known, but maybe instead of describe them, the Kronecker result, I will speak about derived equivalence. So this is our queer Q2. The fact is that derived category of modules over this queer is actually, it's derived equivalent. Bounded derived category is equivalent to derived category of coherent sheaves on the projective line P1. This is from my PhD thesis paper. There's many generalizations of this, but let's consider just this one. So question is what, but of course it's derived equivalence. You have here representations of this QR, Kronecker QR, and you have corresponding subcategory of coherent sheaves here. And this does not mean equivalence between these two guys. One have to be careful about this. So, but about coherent sheaves, it's geometry, so it may be easy for me to describe it. What are, so coherent sheaf has rank. There is, I don't know, the Grothin group of P1, meaning of this derived category, is Z squared, and the map from here to here is given by the rank and the first Chern class, C1, of the object here. So this is the map from here to here, which gives an isomorphism. So all right. So and moreover, all objects in say in the Billion category and in derived category are very well known in this category. Say in the Billion category, every object is the sum of the torsion sheaf and the line and the vector bundle. So every F here has the form F, some torsion sheaf plus locally free sheaf, because it's a smooth curve. And moreover, for P1, every vector, so it's locally free sheaf, meaning it's a vector bundle, and it's actually the sum of the sheaves like O of J, Jk, sum over K, sum of line bundles. And moreover, also every torsion sheaf is known to be the sum of the sheaves of the form O. So you should choose point X in a closed point in our P1 and consider some infinitesimal neighborhood of it, which I will denote by Xn. So it's locally it's isomorphic K of T by Tn, right? So say A1 would be X, right? So it's some infinitesimal neighborhood of this point. So you have P1, we have here a point, we have some infinitesimal neighborhood of this point. And so we can consider the structure sheaf of these guys over some points xi, and here ni, and sum up it over to, I don't know, S. So every torsion sheaf has this form, every locally free sheaf has this form, every sheaf on a smooth curve has decomposed in this and this. So how they look on this, if you consider rank and C1, so this guy's line bundles. We consider only indecomposable objects, meaning this guys and this one. So line bundles are in here. So this is rank, this is C1. So here is O, here is O on 1, on 2, and so on. And also we have rank of these guys is trivial. So we are on this line, and the churn classes are here. So here are skyscrapers, just OX. The next is OX2, and so on. And by the way, they are here parameterized, say here in the composable objects parameterized by P1, and also here they parameterized by P1 and so on. And these objects are exceptional, they are rigid. Just one object in here. And if you consider derived category, then actually not so much extra objects appear, just there is a shift functor in strangulated category, there is a shift functor. Every object actually is the sum of its cohomology, so it's these objects and their shifts and their sums. So in the composable objects are only this, and their shifts. Question? Excuse me? By? C. What is C? All right. Yeah. Mm-hmm. Right. Well, it's a rather simple example. Nevertheless, I told you about this derived equivalence. I'm going to use it to classify. So, for instance, I just show on one example how we can use geometry and derived equivalence to calculate the rank of the object. I hope. So let me consider object F. Yeah, well, first this equivalence where this modulus S0 and S1 go under this equivalence. S1 goes to, say, O01, and the S1 goes to, I mean, these are modules over algebra, and these are coherent shifts, or in derived category. The other one goes to O shifted by 1, because it's not equivalence on abelian categories, so we should do this. And instead of this exact sequences, we should consider triangles. So there are some modules corresponding to these guys. So let me consider first interesting example is the following. When we consider OXN, when the rank is not obvious, and OX, the same point, X0, with another, say, M. So this is our F. And if we reinterpret what I said before about the rank, then it's actually, I mean, we have some module corresponding to it. It's a representation of Kronecker quiver. In terms of the Kronecker quiver, this guy looks like this. You have two vertices, two arrows, right? So you should put something, say, for one of them, just n-dimensional vector space here, Cn. N-dimensional space here, Cn. And these two operators, one should identify one space with the other, and when you identify it with the other, then the other is given, so alpha, you may assume alpha is identity, and beta is the Jordan matrix, say, with whatever x in here. And x is actually, you can see it's actually an element in P1. Because you use, I mean, of course, here x is just an element in just a complex number, so it's in a fine line. But in fact, it's because you should this identity. If you don't require this, then you can see that the moduli space of these representations is P1. And it's the moduli of this, it just corresponds, I described what corresponds to OXN. This representation. Okay? So now, interesting case, when you consider the sum of these two guys and calculate the rank as it's defined there. And it's about the following diagram. So the question actually is clear that rank is not less than so let me even make it more simple, just the same n here. It's clear that the rank is not less than n plus 1. You will see why. But the question is why it's not equal n plus 1. It's actually n plus 2. So let's consider this shift f. Then if we reinterpret all this via this derived equivalence, it's about the following. We consider here the sheaf O1 and consider some extension, say G. So I consider this. And then here we should consider O, short exact sequence like this. And here we should get some sum of the skyscraper. The point is that skyscrapers, I mean, when xi's, the skyscrapers, they are rank 1 in terms of this derived equivalence. I mean, under the derived equivalence, rank 1 representations go into skyscraper. Rank 1 sheaves are exactly skyscrapers. Meaning OX for some X in P1. So basically, we need to present our, dominate our object by the sum of skyscrapers according to this definition. So what we can see here, so I want to show, to explain that this approach gives some low bounds for this rank. So in this particular relatively simple case, and the point is that there is no diagram like this. Well, why is that? The point is that the rank of this sheaf, geometric fiber of this sheaf at this point x0 here is 2. It implies that the rank of this sheaf is also at least 2. I forgot what's the argument. It means well, so the point is that somehow, I mean, these two sheaves, right? Somehow, the point is that at this point, x0, what happens that the rank is 2, it means that you have some torsion in this sheaf G. Yes, because generically this sheaf G is of rank 1, right? So you have, I mean, the rank at the generic point is 1 for this sheaf, because this is torsion sheaf, so this is rank 1 sheaf. But because it has rank 2 here, it has rank at least 2, it could be 3 at this point. So you have some, for G, you have some singularity at this point x0. And if so, because every sheaf on the curve is decomposed into locally free sheaf and the torsion, it means that you have some torsion here. So this sheaf G has torsion because of this F. And then you can see that if you have a torsion and you have a quotient by some sheaf with no torsion, then this torsion survives here. And then you can see that because this torsion is quite big one, this cannot exist here. So you see this kind of geometric argument and theory of coherent sheaves helps to prove. Well, it's actually a classical result. It's known maybe from 50s. But nevertheless, this geometric approach allows to interpret, and direct category approach, to interpret even this. I mean, otherwise there is a lengthy proofs of this statement. So this was some example. And now I would like to formulate a general definition and the theorem. So now I would like to consider arbitrary quiver. Actually, one can consider something more general. Some say A is a abelian category over C linear. Abelian category with the finite number of simples x1 finite, home and x1 finite. I think nothing else is required. Just finiteness condition to concentrate on a really important issue. For instance, this category of modules of the query relations is of this form, but it could be more general. For instance, if you consider K of T formal power series in T, then finite dimensional modules is a category A of this form. This is an example. And it's not representations of a finite dimensional query. And it's exactly the category of sheaves we support at the origin and a smooth point. So it's torsion sheaves we support at the origin. Okay, so it's a little bit more general story. And we can ask then what? We have finite number of simples. Let's denote let's denote them as i's. We can define objects of rank 1. So object M in our category is of rank 1. By definition, if it's like was there, it's an extension of one simple module by another simple module, probably the same one. This kind of thing. So we have. And then we can define the rank of arbitrary object. Yes, I must say that it should be Artinian and Noetherian. Artinian, Noetherian. Meaning every object has filtration by simple, finite filtration by simple object, with simple factors. Artinian. It's already Noetherian, I guess. Anyway. Category. So every object has a filtration. So then we can define the rank of the object M is minimal, the minimal case such that the sum of mi's or dominates I from 1 to k, such that they dominate our module M in this sense, and the rank of mi is 1. So somehow from the Kronecker query or generalized Kronecker query, we come to the arbitrary category with this property. Now theorem is so then we can ask the question when this rank is finite for any object. And this is the theorem. The following are equivalent. Any M in A is of finite rank. And the second statement is that the square of the radical of A equals 0. Here I should say what is the radical. So if you have an object M, well, there is a notion of radical of any element, of any object M. The point is that we have functor from A to A0. A0 is kind of semi-simple part of A. So it's generated by simple objects. So we first functors in both directions. And here, SIs. It's just direct sums of SIs. Simple objects, meaning semi-simple objects. It's the category of semi-simple objects in A. So we have a functor from we have embedding of A0 into here, and we have two adjoint functors. Let me denote this by this embedding by I, and this by I upper shriek and I upper star. Yes, this way. So then it's basically given. So what is this functor from here to here? You have some, say, consider modules over algebra for simplicity. Okay. So if you have a module, then you have the biggest semi-simple submodule, or you have the biggest semi-simple factor. These are these two functors from here to here. So one goes to biggest submodule, the other to biggest semi-simple factor. So because these are adjoint functors to the embedding functors, you have a morphism something like I upper shriek I low star of A0. I mean, it's exactly meaning the semi-simple quotient, if I'm correct, yes. And then you can define the radical of an object as a kernel of this, as the kernel of this map. This will be AP, so it's short exact sequence. M goes to 0. From this short exact sequence, we can define the radical of every object. And basically, it means the square, R squared of every module is 0. Am I time? 2 minutes. Maybe I wouldn't say anything about proofs. Well, examples, for instance. Already the example, when we have one vertex and n arrows from here to here is kind of interesting. So n loops, so to speak, of the one vertex. So what is this property? I mean, if you just consider this quiver, it does not satisfy this condition. But if you consider the quiver, so you require all these alpha i's from for I from 1 to n, right? If you consider quiver with relations that alpha I, alpha j is 0 for all ij, then this does satisfy this condition. So for the representation of this quiver, we have the notion of rank, and the rank is finite for any object. So what is the representation of this quiver? It's geometrically. It's about taking an n-dimensional affine space, an, choose a point, the first neighborhood of this point, and these are just sheaves, coherent sheaves with support, so to speak, schematic support at the origin of this point, at this first neighborhood. So already for this particular case, the rank is kind of very interesting thing, and I encourage people in the audience to calculate this rank the same way as people did it for, I mean, to try to calculate it, because this is already hundreds of pages on calculation of this rank, but this is something new. Thank you.
Thank you for interesting talk. Are there questions or comments? Yes.
In the term, when you define this R, the functor is derived level or the abelian level?
No. This is all about abelian categories.
Okay. Oh, can
I just consider particular case of abelian categories of, I mean, with these conditions.
Okay. Can you repeat what do you mean by R2 equal to R2? R.
It basically means the composition of any two arrows is 0. That means if it's about representation of the quiver.
I see. R squared means R composed with R.
Yeah, R squared is yes, it's square of R. Yeah, sorry.
I see.
Yeah, the point is that if you consider some short exact sequence of modules M1, M2, M3, modules are objects in this category, a bit more general than modules. Then, if you apply this R, then all mono are comes into mono. All AP comes to the AP, but
Okay.
the functor is not exact.
Okay.
It's something very similar what happens with the intermediate, how's it called, intermediate extensions for perverse sheaves. But I didn't make this connection explicit so far. So I think it's about perverse sheaves somehow.
Oh, I see.
But
So R is
I
an
tried
exact.
to think tonight about this, but
You are saying R is an exact functor?
no, it's
No,
not. That's
it-
the point. It's not
that's-
exact. Like intermediate, you know, for perverse sheaves, for instance, if you have some Z topological space X, Z, and U, which is X minus Z, right? Then you have this I, J, and there is so-called J low for sheaves on U. I mean, you have this intermediate extension, J low Schrick star.
I see.
This functor is also preserves sub-objects. I mean, mono goes into mono, AP goes into AP, but when you apply functor, you are not exact in the middle.
Oh, I see.
So this is analogy. I think it should play something in this game. But
Okay, thank you. Sorry, another question. In the proposition above, you define this ideal generated by M. You write it as L1 times M times L2. Can you say again what do you mean by L1 and L2?
here is no L. You mean here?
Yes.
I don't see any L here.
Here.
Here. L1 and L2 are arbitrary objects in our category.
Arbitrary object.
Right. So somehow we start from our object, whose rank we want to define. We extend it. So what does it mean? It means that this N has some filtration. So let me write it. So three-step filtration. This is our N, right? This is a sub-object. The other way. This is sub-object. This is some next sub-object, and this is the whole N, okay?
Okay.
And this piece, I mean, the quotient of this sub-object by this sub-object, this is M.
Okay.
So this we require M extend from both sides in such a way that N decomposed in the sum of rank 1 objects. Strange thing, isn't it? But it's exactly what is about computational complexity.
Okay. That's it. Thank you.
Are there any questions? Yes.
Well, maybe I explain what's the geometric meaning of this fact. I had to say this, but I forgot. Sorry. So, what is the rank 1 matrices or tensors? So we consider, after all, just tensor product of three spaces, right? U star, tensor V star, tensor W. And alpha is here. What is decomposable vector? I mean, let's consider projectivization of this space. U star, tensor V star, tensor W star. So what are decomposable rank 1 vectors? It's just Segre embedding P of U star cross P of. It's a point on the Segre embedding, which is embedded into here. So these are rank 1. What are rank? Our multiplication is just some particular vector element in this, some point in this big projective space. And we consider Segre embedding of three guys into there. So we have a point, we have this Segre, and now we are looking for some k secant. K secant meaning you consider k points here and consider the projective plane generalized by them. And our point should be in there. This is how algebraic geometry try to solve this problem, to calculate the secant variety. And in particular, for 2 by 2 matrices, there is a particular way how you can do it. But by the way, it doesn't need to be unique. I mean, Strassen written down particular thing where you just use only plus and minus signs to write them down. You don't need complicated computations. But to write it down explicitly, you know. I should write down seven bilinear forms, and there are linear and 8 linear combinations of them, which we give you now. It just takes too much time, and I don't remember.
Thank you.
Yeah, that's what computer can do in principle. Yes, but I don't think they can. They can find, say, the low bound, like what I did in this most simple example, using some geometry. Yeah.
Oh, yeah, maybe you have explained this. So the coordinate quiver corresponding rank 2 case, can you write the multiplication, the tensor phi in terms of coherent sheaves on P1? Which one is that?
I mean, what your question is? What is this equivalence?
Yeah.
Yeah.
Under this equivalence, what is the M representing the tensor of 2 by 2 matrices?
M is F. M is F. So we consider extension. So O1 corresponds to one simple modulus. This guy corresponds to the other one, right? So we should extend F by O1 on the one side. It makes no sense to extend by the other simple on the other side because it would be trivial extension. So we basically F consider star F and star F O on O. Here it's O on 1, and here O shifted by 1. So this extension is actually here. If you consider this exact triangle further, then you got O shifted by 1 here. So first you extend F by O1, and then you extend G by O1 on the other side. So this guy, which should be the sum of skyscrapers, rank 1 guys, it's extension here. So I just removed it, but I just wrote in the category of coherent sheaves.
So F is a direct sum of these two guys.
This is the direct.
I mean, top.
Here.
I mean, F is this guy.
F is this one, right?
Okay, so is it n equals 2? I mean, I would just ask is that n equals 2? Like, I'm just asking a very explicit case.
Yes, for instance, you can take n equals 2. It's already. So the argument was to show that just one extension is not possible. If you extend with O1 squared and O squared here, you can easily construct this construction. I mean, you can make it. But with one, it doesn't work for geometric reason. I mean, in principle, for any F, for any object of the category, you can calculate this rank, and it's just long formula, but you can write it down. I just wanted to show in this particular example how derived categories and geometry of coherent sheaf helps to prove this.
Okay, thank you.
Okay, let's thank the speaker again. We resume 2:15.